Every second, a portion of the electricity humanity generates is lost as heat. Not because of bad design, but because electrons cannot move without resistance. They collide, scatter, and waste energy into the material itself. This is not a flaw in our technology. It is a limit imposed by physics. Inside any metal, electrons don't flow freely. They move through a vibrating atomic lattice, constantly interacting with thermal motion. Each collision transfers energy into the structure as heat. Globally, this effect leads to significant energy loss across transmission systems and electronic devices, an invisible inefficiency built into the fabric of matter. But under certain conditions, that behavior changes completely. At extremely low temperatures, thermal vibrations drop. Electrons begin to form correlated pairs known as Cooper pairs, which move through the lattice as a unified quantum state. Instead of scattering, they propagate coherently. The result is superconductivity. Electrical resistance falls to zero, not reduced, eliminated. And with it emerges another phenomenon, the Meissner effect, where magnetic fields are expelled from the material, allowing stable levitation above its surface, a direct consequence of quantum order at macroscopic scale. There is a constraint. Most known superconductors require temperatures near absolute zero, sometimes below -250 degrees Celsius. Maintaining these conditions demands complex cooling systems, limiting widespread use. This is why superconductivity remains largely confined to specialized environments, MRI systems, particle accelerators, and experimental physics. The real objective is far more difficult, a material that can superconduct at room temperature and practical pressure. Across the world, researchers are searching for that material. Some experimental compounds, particularly hydrogen-rich systems under extreme pressure, have shown promising behavior. Other claims have sparked debate and ongoing verification. The challenge is not just achieving superconductivity, but stabilizing it, reproducing it, and scaling it into reality. This is not a solved problem. It is one of the most intense scientific pursuits of our time. If that barrier is ever broken, the implications would be immediate. Power grids could operate with near-zero transmission loss. Electrical systems could become dramatically more efficient. Magnetic levitation transport could expand beyond experimental lines. And in fusion research, superconducting magnets could play a critical role in controlling plasma at extreme conditions. Energy, stored and transmitted with minimal loss, would reshape infrastructure at a global scale. Resistance appears fundamental. Constant cost of motion through matter. And yet, under specific conditions, it vanishes completely. Not weakened, not minimized, gone. So the question is resistance the rule or just a limitation we have not yet learned how to escape?